Welcome to the channel. Today we address a question sent by email. How can we determine the optimal heat treatment for a specific additively manufactured aluminium alloy and for a specific application? Determining the optimal heat treatment for a specific additively manufactured aluminium alloy, tailored to a particular application, necessitates a nuanced approach. The process hinges on understanding the unique microstructural attributes inherent to additive manufacturing alloys and how these characteristics influence their response to heat treatment. The distinctive microstructure of additive manufacturing aluminium alloys stems from the rapid solidification rates typical of additive manufacturing processes, particularly laser powder bed fusion. These conditions result in microstructures that significantly deviate from those observed in conventionally manufactured counterparts. A key characteristic is the presence of a supersaturated matrix in the as-built state. This inherent supersaturation negates the need for a solution heat treatment, a step typically employed in conventional processing to dissolve alloying elements into a solid solution. Conventional heat treatments, such as the T6 treatment, which involves solution heat treatment followed by artificial aging, are often ill-suited for additive manufacturing aluminium alloys. Applying a solution heat treatment to an already supersaturated additive manufacturing microstructure can be counterproductive. It can lead to undesirable grain coarsening, diminishing the beneficial effects of the fine-grained structure produced during the additive manufacturing process, thereby negatively impacting the final mechanical properties. Direct aging, also known as T4 treatment, emerges as a more appropriate heat treatment strategy for additive manufacturing aluminium alloys. This single-step process focuses on relieving residual stresses within the material and promoting the controlled precipitation of nanometric secondary phases from the supersaturated matrix. This precipitation process is crucial for enhancing the strength of the alloy. Direct aging offers the added advantage of circumventing the water-quenching step inherent to the T6 treatment. This is particularly beneficial for additively manufactured parts, which often incorporate complex geometries and thin walls, as water quenching can induce unacceptable levels of distortion. The specific application dictates the desired mechanical properties, which in turn guides the selection of the optimal heat treatment parameters. For instance, if the application demands high strength, the T4 heat treatment should be optimized to maximize the precipitation of strengthening phases. This typically involves aging at a specific temperature for a duration that allows for the formation of fine, dispersed precipitates. Conversely, if the application prioritizes ductility over peak strength, a different set of T4 parameters, potentially involving a lower aging temperature or shorter aging time, would be more suitable. Computational modeling tools, such as those based on the CALF-HAD calculation of phase diagrams approach, play an increasingly important role in optimizing heat treatments for additive manufacturing alloys. These tools enable the prediction of phase transformations and precipitation kinetics under different heat treatment conditions, reducing the reliance on time-consuming and costly experimental trials. For instance, by simulating the precipitation behavior of strengthening phases in a specific additive manufacturing aluminium alloy, CALF-HAD modeling can aid in identifying the T4 treatment parameters, temperature and duration, that would yield the desired precipitate size and distribution for the intended application. In a nutshell, determining the optimal heat treatment for a specific additive manufacturing aluminium alloy for a specific application is a multifaceted endeavor. It requires a thorough understanding of the unique microstructural features of additive manufacturing materials, the influence of different heat treatment strategies on these microstructures and the specific mechanical property requirements dictated by the intended application. Computational modeling tools are becoming indispensable for streamlining this optimization process. Thank you for joining us today. For more insights on metal additive manufacturing, subscribe to the channel and visit our website at insidemetaladdivemanufacturing.com.